house up to a satellite orbiting 550 kilometers outside Earth's atmosphere. Well, let's be honest, around 27,000 kilometers per hour, and data is being sent back and forth between them at hundreds of megabits per second. All while the dish as to how this is possible. Stick around, because we're going to dive into the multiple key technologies which enable satellite internet to magically work. First, we'll exactly the dish and satellite are sending inside the beam that results in your ability to stream 5 HD movies or shows simultaneously. This video is quite. We recommend watching it first at 1.25 times speed, and then a second time at 1.5 speed to understand it, and clarifying the difference between a television satellite dish, such as this one, and the Starlink ground dish, which Elon Musk dubbed Dishy McFlatface, or Dishy for short. TV dishes use a parabolic reflector to focus the electromagnetic waves, which are the TV signals sent from broadcast satellites orbiting the Earth at an altitude of 35,000 kilometers. TV satellite dishes only receive TV signals from space. They can't send data. Dishy, however, both sends and receives internet data from a Starlink satellite orbiting 550 kilometers away. Starlink satellite need to be focused into tight, powerful beams that are continuously angled or steered to point at one another. Compare this to Thus, 10,000 or more Starlink satellites, all orbiting at incredibly fast speeds in a low Earth orbit, are required to provide satellite internet to the entire Earth. Let's now open up. We have a pair of motors and an Ethernet cable that connects to the router. Note that these motors don't continuously move Dishy to point directly at the Starlink satellite. They're used only for initial setting. We find an aluminum structural backplate, and on the other side we find a massive printed circuit board or PCB. One side has 640 small microchips and 20 larger microchips organized in a pattern with very intricate traces fanning out from the larger to smaller microchips, along with additional chips including the main CPU and GPS module on the edge of the PCB. On the other side are 1,400-ish copper circles with a grid of squares between the circles. Behind that, we find another honeycomb pattern, and then the front side of Dishy. So, what are we looking at? Well, in essence, we have 1,280 antennas arranged in a hexagonal honeycomb pattern, with each stack of copper circles being a single antenna controlled by the microchips on the PCB. This massive array works together in what's called a phased array in order to send and receive electromagnetic waves that are angled to and from a Starlink satellite. Here we have an aperture-coupled patch antenna composed of 6 layers, most of which are inside the PCB. It looks very different from the antenna of an old-school radio and is honestly incredibly complicated. So let's simplify it. We'll remove a few of the layers for now and step through the basic principles of how we generate. At the bottom, we have a microstrip transmission line feed coming from one of the small microchips. This transmission line wire that abruptly ends under the antenna stack. We send a 12 gigahertz high-frequency voltage or signal to the feed wire, which is a voltage that goes up in your 60 hertz household electricity. For example, above the copper to it, called an antenna patch. With DC or low-frequency alternating current, there wouldn't be much happening because the patch is isolated. But with a high-frequency signal, the power sent to the feed wire is coupled. Gigahertz signal is applied to the copper feed wire. Orbital, or trough, we have a concentration of electrons pushed to the end of the feed wire, thus creating a zone of negative charge, which corresponds to the maximum negative voltage. This concentration of electrons on the tip of the wire repels all electrons away, including the electrons on the top side of the patch becomes positively charged, while the other becomes negatively charged, thereby creating electric fields between the patch and feed wire, like so. However, when we reverse the voltage to the copper feed wire 42 picoseconds later, we have a concentration of positive charges, or a lack of electrons at the end of the wire, and thus the electrons in the patch flow to the other side, the voltage in the patch is flipped, and the direction of the electric fields are also flipped. Because the feed wire voltage oscillates back and forth 42 picoseconds between one peak and trough, the electric fields in the patch will also electric field vectors or arrows from the patch are vertical, and because they're equal and opposite, they cancel out. However, other electric fields are horizontal in the same plane of the patch and are called fringing fields. These fringing fields are in the same direction and at the same time, electrons flowing from one side of the disk to the other, which is an electric current, generate a magnetic field with a strength and direction and a magnetic field pointing perpendicular to that. Let's move forward in time to where the voltage on the feed line becomes positive picoseconds later. The charge concentrations, or voltage, as well as the current, is all flipped. Electric and magnetic fields propagate in all directions, and by creating these oscillating fields, we've generated an electromagnetic wave, which travels in the direction perpendicular to both the electric and magnetic field vectors. Because the two sets of field vectors are not all in the same plane, opposite direction. Additionally, the strengths of these field vectors directly relate back to the voltage and signal that we originally sent to the copper microstrip feed wire at the bottom of the stack. Which means, if we want to make these electric and magnetic fields stronger, we just have to increase the voltage. Thus far, we've been as transmitting. However, it can also be used for receiving a signal. In this microchip, called a front-end module, we switch the antenna from transmit to receive and turn off the 12 GHz signal when an electromagnetic wave from the satelliting flow of electrons. This received high-end module chip which amplifies the signal. Thus, these antennas can be used to both transmit and receive electromagnetic waves, but not at the source, and is more complicated than we've discussed. For example, here are two circular patches. The bottom is used to transitionally. There are two H slots and two feed wires to support circular polarization, a reflective plane in the back, and also there are multiple features for isolating the operation of one antenna from the adjacent antennas. We've included these and many more details in the creator's comments, which you can find in the English-Canadian subtitles. The second note is that there are visible light from the sun, radio waves from radio or cell towers, or TV signals from satellites or towers. Therefore, in order to block out all other frequencies of electromagnetic waves, the antenna is only a centimeter, the light a few thousand times brighter, and then focus all the electromagnetic waves into a single, powerful beam. PCB. 55 centimeters wide, with a total of 1,280 identical antennas forming. So, how does it work? Well, let's first see what happens when we had before. One antenna generates an electromagnetic wave that propagates outwards in a balloon shape, at every single point in space, pointing in the same direction with overlapping peaks, and thus add together via constructive interference, and in other locations, they're opposite with one peak on one trough, and thus they cancel each other via destructive interference. We can now see that the zone where they add together constructively is far tighter, or more focused. Adding 1,280 antennas together, we can form a beam with so much intensity and directionality that it can reach outer space. 1,280 times over would result in a combined power range of the main beam from all these antennas combined is a single antenna, multiplied it by 1,280, and then placed a whole bunch of mirrors around it and left only a single hole for the main beam to exit through. The long explanation requires a ton of math and physics, so let's move on. Dishy McFlatface and the Starlink satellites undoubtedly have some rather complicated science and engineering inside, and to fully comprehend it all, you have to help you do that. Cars, quantum computers, rocketry, or neural networks. For example, they have an entire course dedicated to waves and light, and another one on gravitational physics, which will greatly help in understanding Starlink and SpaceX rockets. Brilliant is technologies, and to help you become a revolutionary engineer and entrepreneur like Elon Musk, you have to be versed in a wide range of fields in science and engineering. We're exploring how a powerful beam can be continuously swept across the sky, and then how we fill it with hundreds of megabits of data and we fed them all with the same 12 gigahertz signal in order to create a laser-like beam propagating perpendicular. The motors isn't feasible because they would break within a month and aren't accurate enough. So the solution is to use what's called phased array beam steering. Let's go back to our two antennas. Shifting is measured in degrees between 0 and 359, because if we shift the signal 360 degrees, or one full wavelength, then we're back at the beginning, exactly as if we were to loop around a circle. For example, here's a signal with a 45-degree phase shift. Here's another with a 180-degree shift, and then another with a 315-degree shift. Your eyes can't see differences in phase-shifted visible light. However, high-tech circuitry such as what's inside Dishy is really good at detecting and working with phase shifts. So then, how do we use phase within a 100-degree field of view? Let's move back. In order to know the exact angle the beam needs to be pointed or steered, we use the GPS coordinates of Dishy from this chip over here, along with the orbital position of the Starlink satellite, which is known in Dishy software. The software computes the exact set of 3D angles and the required phase shift for each of the antennas. These phase shift results are then sent to the 20 larger chips called beamformers, and each beamformer coordinates between 32 smaller chips called front-end modules, each of which controls 2 antennas. Every few microseconds can be steered anywhere in a 100-degree field of view. There are a few quick notes. First, the main beam, also called the main lobe, looks like this. However, constructive and destructive interference isn't perfect, and as a result, are used to communicate with the ground stations to relay the internet traffic. And fourth, phased arrays are used in many applications, and interestingly, they're used on commercial airlines to allow for mid-flight internet. So this video also tangentially explains how mid-flight internet works. Before we exit, if your mind is blown by the complexity of this technology and the depth of this video, click the subscribe button, like this video, write a comment below, and we'll